Hi everyone, thanks for attending my talk. My name is Benji and I'm one of the core contributors to Pants, which is an open source build system. And today we're going to talk about Python codebase architecture and specifically about monorepos. Before we dive into that, just a little bit about me. I've had over 25 years experience as a software engineer in the industry. I've had the good fortune to work at some really cool companies, including my first job was at Checkpoint in Tel Aviv. And as I mentioned, I'm a maintainer of the Pants open source project. And for the last few years, I've been the co-founder of Toolchain, which is a startup in the build system space. And a quick overview of this talk, we'll start by addressing, well, what is a monorepo? What is this thing I'm talking about? Then I want to address why would you want a monorepo? And finally, we'll talk a little bit about what kind of tooling you need to work effectively in a Python monorepo. So let's just jump straight into what is a monorepo. So to talk about monorepos, we have to talk about codebase architecture. Now, the common characteristic of almost all codebases is that they grow over time. Now, they grow because each developer working on a code base keeps adding code over time. But also, if you're hiring, then you're also adding more developers, and each of them is writing code at a certain rate. And so overall, your code base can grow more than linearly over time. And this causes a problem. A common consequence of this growth is that your builds get harder. They get slower and they get less manageable. Now, I can already hear that some of you are objecting in your minds and saying, well, this is a Python conference. We're talking about Python code. Python is not a compiled language, so what do you mean by build? So I should clarify that by build, I mean build in the general sense, all the steps that you take to go from writing source code all the way through to having a deployable artifact that you can push to production. So everything that happens from when you hit save in your editor. So that can include steps like resolving and downloading external dependencies, generating code if you use code generators like Protobuf or Thrift, type checking. Python is not compiled, but it does now have a very robust and useful type checker in MyPy. Running tests obviously is a very big build step. Debugging, running linters and formatters, packaging, so actually creating that deployable artifact, whether it's an sdist or a wheel or a PEX file or an AWS Lambda. So I think you'll agree that even though there is no compilation step in Python builds, there is definitely a build and it contains a great many steps. And these builds are exactly the things that get slower and less manageable as the codebase grows. So what do we do about this? We end up having to make one of two architectural choices, and I refer to these as multi-repo and monorepo. And we'll start by talking about multi-repo. So the multi-repo architecture is when, as your codebase grows, you split it into growing numbers of small repos, and you split it usually along project boundaries or library boundaries or team boundaries. And this very often happens because it's the path of least resistance. The Python toolchain, in ways that we'll see, kind of pulls you in that direction a little bit. But there is an alternative, and that is what we're talking about today. The alternative is the monorepo architecture. And a monorepo, as I'm defining it, is a unified codebase containing code from multiple projects worked on by multiple teams that share underlying dependencies and data models and other functionality. So, for example, a monorepo may contain code written in multiple languages. It may contain code that uses multiple frameworks. So you may have some code in a monorepo that uses Django and other code that uses Flask. You may have, as I mentioned, different teams or different parts of your organization working on separate parts of the monorepo, but they very often overlap, particularly on these shared dependencies. But the general idea is that as your organization grows and your code base grows, your monorepo grows right along with them. Now, I should emphasize, because this gets asked a lot, we're talking about code-based architecture, not deployment architecture. So a monorepo code base is agnostic to whether you deploy monoliths or microservices. And in fact, monorepos are often really great and frankly a better solution for microservices, precisely because microservices very often share so many underlying dependencies, and they share an infrastructure, and a monorepo, as we'll see, is often a really good way to manage that. So we've covered the definition. We've explained what monorepo is and how it contrasts with the alternative of multi-repo. Now we get to the meat of this talk, which is, well, why should I want a monorepo? And I will admit that multi-repo does sound better at first. It's more decentralized, it's more bottoms up, it allows more local control, and it's also really tempting because it lets me kind of put a barrier between my perfect repo and all those other barbarians. So I can protect my code, or my little team can, and if anyone else wants changes, they have to come through me. So multi-repo can be really tempting, and it does sound better. But the trouble is that things that sound good in theory become a problem in real-world scenarios. And in particular, in this case, there are some core code-based management challenges that multi-repo seems like it solves, but actually not only does it not solve them, but it hides them, it pushes them down the road, and instead it creates a new set of problems. And at least monorepos make these challenges explicit and force you to deal with them instead of kicking them down the road. And let's look at exactly what I mean by this. So the code-based management challenges that I'm talking about have to do with managing changes, managing dependencies, and most importantly, the overlap between both of those things. Managing changes is hard, but managing changes in the presence of dependencies is much harder. And vice versa, managing dependencies is hard on its own, but managing dependencies in the presence of constant change is much, much harder. So that intersection in the middle there is where a huge amount of code-based management pain lives. So let's look at how these challenges have to be handled in the multi-repo case. So multi-repo architecture relies on publishing. For code from some repo A to be consumed by some other repos, it has to publish an artifact, such as an sdist or a wheel, that those other repos can consume. Now, I should emphasize that publishing in this case probably means to a private internal repository, because we're talking about how to organize your internal code base, your team, your organization's private code. How to share code publicly on the internet, for example, in open source across many different organizations, is a separate topic, obviously related, but not one that we have time to get into today. Although I have opinions about that as well, as you can imagine. So multi-repo relies on publishing, even if it's internal publishing. And of course, unless repo A in this example never changes, and when do we ever have code that never changes, these artifacts need a versioning scheme. So for example, when repo A makes a change, it has to republish itself under a new version. Why? Because otherwise the changes might break existing consumers of repo A. So let's say now repo B depends on repo A, and remember, we're still talking about the multi-repo example. So repo B depends on repo A at some specific version. And now let's say you're the author of repo B and you need a change in repo A. You're relying on its functionality. You need to modify that functionality in some way. So you have to modify A, you have to publish it at a new version, and then you have to consume that new version. And this is assuming that you are able to make changes to A. If not, you have to find the owner of A and convince them to either make the changes or let you make the changes. But again, let's assume you've made that work. Now, having made the change to A, you have two choices here in sort of how to handle that change. The first is the virtuous choice. This is when you want to be a good citizen. What you would do in this case is you would go and find all the consumers of repo A. They include your repo B, but they include possibly many other repos. And you ensure that they still work at this new version. And you make changes until you're convinced, say, because tests pass, that every single one of those consumers works with the new version of A. And now, that was a lot of work, but are you done? You are not done, because you've made changes to other repos now. And so now you have to recursively find the consumers of those repos, and you have to verify that they work with these changes, and so on recursively. This is a lot of work. So for every single repo, you have to first of all find the consumers of that repo, and that is hard to do. Think about it. In the metadata of repo A, there is no information about who consumes A. That metadata lives on the consuming side, not on the side of the repo being consumed. So you have to somehow grok all of the repos in your organization to see if any of them depend on the repos that you've changed. Then you have to figure out how to verify that the upgrade works. So for every one of these repos, you have to know, for example, how to run its tests or how to otherwise qualify it. And then you have to keep doing that recursively. So this is a huge amount of work. And so that leads a lot of people to, the lazy choice, which is, I'm not going to worry about the other consumers of repo A. They're safely pinned to an earlier version, or at least let's hope they are. And we'll just let those repos deal with the problems when they upgrade. And that is easier for you, but it's also not very nice. These are your coworkers, and by the time they upgrade, they may not have the context for your change. You may not even remember the context for your change, or you just may not be around anymore, or you may not be interested in helping them. So you've really kicked a problem down the road. And what is the magnitude of that problem? Well, so what this problem is essentially a version of the famous dependency hell problem. This is the problem that in the JVM world is called jar hell. And the problem is that unless all of your repos update themselves to new versions in lockstep, you end up with these collisions where, because you can end up depending on the same repo transitively through multiple paths, you may end up having to pick between two conflicting versions, and it's possible that neither of them will work. Even if one of them does work, you don't necessarily know which one. So this is what I mean by multi-repo hiding problems. It essentially allows you to push responsibilities off onto other people in the future, and you're leaving like little time bombs in the codebase that were set to explode in the future when someone needs to upgrade. And that is not a great way to run an engineering team, having people able to trip other people up in this way, just so they can make short-term progress. So that was all multi-repo. Now let's look at how change management happens in a monorepo. In a monorepo, there is no versioning and there is no publishing. And again, I'm overlooking for now the issue of how code might be consumed externally. This is all within an organization. So within that context, at least, there is no versioning and no publishing. All the consumers of library A are right there in the same repo along with it. So you can find who all those consumers are with ripgrep or whatever tool it is you use to grok your code base. Breakages are immediately visible because you can just run all the tests in the repo or all the tests that might be affected, and you can immediately see what the global impact of your change is. So the codebase architecture itself here enforces responsibility and good teamwork. So we've seen an example here of how monorepos are actually more flexible. So even though it seems counterintuitive, they actually provide a lot of alternatives, a lot of flexibility compared to the alternative that allows you to move faster and break less things. So there are other advantages to monorepos that fall along similar lines. For example, they are easier to refactor, and you have a unified change history. It's easier to reuse code because it's all just sitting there in the same repo. We could give a whole load of examples there. We don't have time to get into that in this talk. But one thought I wanted to leave you with before we move along is that your code base and how you organize it is a reflection of your team and how you organize that. So it's true that there are cases in life where local sort of bottom-up decisions are desirable, but that is not how we want to run our engineering team. In a well-functioning organization, I would argue priorities and decisions and effort allocation flow from the top down, and everybody has a unified goal. And so the code base is a reflection of the organizing principles of your engineering team. And many large companies have adopted the monorepo architecture to keep their organizations unified even at huge scale. And one of the biggest examples of this is Google, that just has a monorepo of just almost mind-boggling size, billions of lines of code. But they keep it that way because it enforces a sense of unity within the organization. So, having talked about what a monorepo is and why we might want one, we move along now to, okay, what tooling do I need to work effectively in a monorepo? So why is that even a question? Why is this a problem? So standard Python tooling, I'm talking about things like pip and PyTest and MyPy and Pylint and whatever tools you're using, they're not really designed for monorepos. When you use them naively, they tend to do a lot of repeated work because they kind of expect that the unit of work is the entire repo. So small changes can end up triggering massive rebuilds. And so as your code base grows, so do your build times. So we need to speed things up. That is the big challenge in a monorepo. Now, how do we speed things up? And this is a very general statement, but really there are two ways. If you have like a large set of work that needs to be done, there are two ways to speed it up. One is do less work, and the other is do more of the work at the same time. Now, to do less work, we need two pieces of functionality, two features. We need fine-grained invalidation, which is really just a fancy way of saying the ability to break the work down into lots of small pieces and know when those pieces need to be run. And then we need caching, because obviously if a task, one of those small fine-grained tasks, has been done before, either by you or by someone else in your organization, it's a complete waste of effort to do it again. And when it comes to doing more work at the same time, then again, there are two features that tie in closely to that ability. One is concurrency, that is the ability to look at tasks and figure out which can run at the same time because they don't depend on each other. And then the final feature is remote execution. Concurrency is great, and if you're running everything on your laptop, you may be able to run 8 tasks at the same time because you have 8 cores on your laptop. But what if you could run 100 at the same time on a cluster? You can see how that would speed things up dramatically. So these are the core features that enable the speed-ups that we want in a monorepo build system. So what kind of tooling has these features? The standard Python tools do not, for the most part. So to work effectively and performantly, you need a build system that is designed for monorepos. And this build system sits on top of the existing standard Python tooling, all the, like I said, PyTest, MyPy, Pylint, pip, whatever it is. And it interprets user requests, it mediates between user requests to the orchestration of when those tools need to run. And there are quite a few tools in this family. Here are some examples. Now, I'm, as I mentioned, one of the core contributors to Pants, so I'm naturally biased towards it. And I should mention that Pants was specifically designed for Python use cases. So it's really worth, I think, looking at if you have a Python code base, but all these systems are great and they're all worth looking at. And they tend to work roughly in similar ways. And we're going to dive into just kind of the common threads in the design of these systems that will also help you when you look at them and possibly evaluate them. So, how do these tools work? There are many, many interesting aspects to them, but three that I've decided to single out. One is that they have goal-based command interfaces. The second is that they rely on build graph metadata. And the third is that they run work using a extensible workflow that doesn't rely on side effects in the file system. And so these features make these systems very different from legacy systems like Make that you might be familiar with. So let's start by talking about the goal-based command interface. So a monorepo build system typically supports requesting that various goals be achieved or completed on specific inputs. So you don't say, for example, run PyTest. You say, I want to see test results for the tests in this file, or I want to get all the packages built for all the packages that are defined under this directory, or I want to run linters and formatters on all the files that have changed in Git. And this is important because the system needs a level of indirection between the actual running of tools, which is how we're used to working outside of the monorepo context, and what it is the user's actually trying to do. And this is important because that gives the system the opportunity to say, actually, I already have a result cached for this, so I don't need to run it again. Or I can tell that these things can be run concurrently, so I will. So we need this layer between what the user wants to achieve and the actual running of processes, which is expensive and which is something that we try to avoid. So the other interesting aspect is, as I mentioned, the concept of a build graph. So there's a lot of information about your source code that you can't derive just by looking at the file system, at the structure of the file system, because the file system is a tree. But your code, if you think about your code as a bunch of units of code, whether they're packages or modules or functions or classes or whatever, and the dependencies between them, they form a directed graph. And you can't derive the information about that directed graph just by looking at the file system. So monorepo build systems use the extra metadata, typically in files literally named build, all uppercase, to figure out what are the units of code and what are the dependencies between them, or in other words, what is your build graph. Some tools require a lot of explicit metadata, and others can infer it by looking inside your source file. So for example, Pants can infer most of your dependencies just by looking at import statements. But either way, all these systems require information about the build graph. Now, they all also have information about the data dependencies between the tasks. This is sometimes called the rule graph. And this is what are the units of work and the dependencies between them. And you can also, this is where extensibility comes in. We all usually have custom build steps that we need to run, and so these can be plugged in typically into this rule graph. But the main important idea here is that instead of relying on side effects in the file system like Make does, these systems explicitly map outputs to inputs. And when you combine the knowledge about code dependencies with the knowledge about task dependencies, you can create this side effect-free workflow where you have these large numbers of tasks that recursively map initial inputs to final outputs, where the final outputs are the goals the user requested, and the initial inputs are things the system can receive from the outside, like the contents of the file system. And we don't have a lot of time to get into this, but if you think about it, having all the inputs and outputs explicitly modeled in a workflow graph is exactly what enables those 4 performance features that we talked about. So you can invalidate subparts of that graph by seeing which inputs have changed and how those changes would flow through the graph. You can cache individual tasks in the graph because you know exactly what their inputs were and you can fingerprint them. You can reason about concurrency because you can look at any two tasks and say whether they depend on each other in the graph or not. And you can even apply remote execution because each of these tasks explicitly defines all its inputs. And so these features are what makes builds scale with your code base. So to sum up, monorepos are an effective code-based architecture. They do require appropriate tooling, but that tooling exists and is really interesting and worth looking at. So thank you so much for attending my talk. I'll be happy to take any questions in the breakout room. I will post a link to that in the chat. So feel free to hop in there right now. And we are also always happy to answer questions at this URL. And we hope to hear from you soon. Thank you again.